So we are looking here at a video of Tom Pay walking around Willesden Junction, which is a train station on the London Overground that we've been working on and doing some pilots with over the last few months. We're looking here at a video on the right, and on the left, the main area, we're looking at a map where we're seeing in real time how the trace algorithm works. So the blue particles are samples. They are samples of where we think Tom could be, and then the coloured particles in the middle are the calculations of where we believe that Tom is actually at any one time. So there are about 5,000 of these blue particles that we generate each time. They're generated using all of the data from the mobile phones, all of the accelerometers, the magnetometers, the barometers, and so on. And then there's a calculation that's done in real time as Tom walks around. So this video is being generated from all of the IMU data, the raw sensor data that's been collected during Tom's walk, and it's being generated on the PC. But normally this algorithm would be running on the mobile phone in real time. The red particle is what we call the best particle, so that is the most likely position for Tom in most circumstances. The other two particles are effectively, the other two coloured dots are effectively the centroid of the overall cloud of particles. And what we've just seen here is Tom walking around a platform, and he's about to turn left and walk down some stairs. And you can see how the blue particles here are sampling the various different spaces, and then as he starts to go down, he turns left, and then he starts to go down what is then a narrow channel down the stairs and under a walkway to the next platform. Now, one of the things you'll spot here is that the broad cloud of particles has been significantly narrowed. It's been narrowed by the walls on either side of this particular walkway. And then this is a technique called map matching, where any particle that tries to go on the wrong side of a wall gets culled from the overall population and replaced by another one. And so we use that to trim the potential positions for Tom, and we use that to continually learn how Tom is walking. So this is not using GPS, this is only using the IMU sensors, the motion sensors on the phone as we're doing this calculation. And as you can see, what we're doing is we are calculating where Tom is as he's walking along. Each time we go up some stairs, we have effectively an artifact that we can see in the data, and that allows us to trim the calculation. Now, if we're going along a long, straight corridor, it would be very easy for that to race ahead. So what we do is make a calculation of how much energy Tom is putting through his hip to estimate his step length as we go, and then we use this map matching technique to help trim that. And as he starts to go down the platform here, what you'll see at the bottom of the platform, or the bottom of the stairs rather, that the particle cloud will then spread out, and it will obviously take advantage of the potentially the larger space that Tom could be in as he's walking around. And this is why you'll see that actually one of the key things that we need is obviously we need good map data. But the beauty of this is that's the only thing that we need. We don't need any local infrastructure. The only thing that's actually guiding this algorithm is Tom's movement and the map data as we're walking along. Now, what you can see here as the cloud has got wider is there's a divergence between the best particle and the centre of the cloud. And that's because we're sampling the whole width of the platform, but we're using the best particle as Tom's current location. And not in all cases, but in most cases, a situation like this, that is the right way to do the calculation. And there's an interesting element here. As the platform narrows, the cloud is sampling the stairs that are right in the middle there as Tom's just walking past those stairs, and it thinks that Tom might be on those stairs just for a few seconds, and then it calculates that there's no height change and that the overall particle cloud should go around that, and then it quite quickly self-corrects for where Tom is actually, and then you can see there that we've picked it up and we've worked out exactly where he is, and he hasn't gone up those stairs. Now, if you just look to the top right of this figure here, you're seeing a round dial. And that round dial is showing us some other information, not just the position, which is the main map, but this is information about where Tom is walking, which direction he's walking in. So the black cloud element in that dial is an estimate of his step length, the radial distance, and then the solid red line is the direction that the phone is pointing in. And then the dotted lines are the directions that the algorithm believes that Tom is actually heading in as we're walking. That is coming as a consequence of the map matching and the selection of the best particles. So the red line there, red dotted line, is the direction from the best particle. So you can see how these are moving around as Tom is moving around. And this information all comes together to calculate how Tom is moving. Now, the beauty of this is our understanding of heading for a worn device is actually really, really accurate. And we've used this in a number of situations to be able to determine which direction someone is in, to be able to give them more information. But also it's a vital part of the information we use when we give someone instructions. We know pretty well which way they're heading in order to be able to say turn left or turn right. Now, as we see here, Tom is now entering a sort of narrowed space as he's walking up the stairs. The best particle is progressing up the stairs and then tends to jump across landings. So we use the global average for that. Now, just at the top here, what you will see is that Tom will turn right and the best particle will get caught a bit behind. This is perfectly normal. It's what would happen in some situations where the map is trimming the situation. So what we've seen is that the heading and the map has allowed us to correct. So this, a bit like the stairs earlier on the platform, what we're seeing is that the trace is actually a really resilient algorithm, and the breadth of the particle cloud, the 5,000 particles, are what gives us this resilience in lots of situations. And then it self-corrects and we're able to follow Tom as we go. So the key here is that we have at our fingertips the accuracy that we need to be able to give the instructions to lead Tom safely around Willesden Junction station. Now we'll see at the top of the stairs here, he'll turn right and he'll go onto the platform and then go around the building in the middle here. So you will note that the map in the middle on the left is showing a sort of a number of lines where on the left, in reality, it's a solid wall. This was just part of a sample test that we were doing to see whether a complex set of walls would confuse the algorithm. And in the main, they don't, not at all. So we're actually very pleased with that result. And it's showing that we have this resilience for complexity of the map environment as well as the individual as well. So I think we're just coming to an end here. And I hope that's given you a good insight into how trace works. Thank you very much.